Hello, thank you for attending this talk today. My name is Dominic Messina, and I will be presenting work done in our research group by my advisor Helen Durand and my colleague Henrique Oyama. This will be a joint talk with Dr. Helen Durand presenting several slides later in the talk. The title of this talk is Interpretability for Moving Towards Verification of Advanced and Data-Driven Control. In this, we will talk about multiple methods meant to increase the confidence an engineer has in their control design. To begin, I will give some background as to why we believe interpretability is important for verifying a controller's performance. For many cyber-physical systems, such as in robots and chemical processes, safe and autonomous operation is a key goal. Theoretical control methods can provide strong stability guarantees when operating these processes essentially autonomously. However, it can be difficult to design a controller to meet all the conditions needed to guarantee stability, and even more difficult to verify its safety when it is online. One key component of our talk revolves around the ability for a controller to self-update according to changing process dynamics, and identifying a new controller in a short time we feel is essential for safe and autonomous operation. However, the controller must update in a way which is understandable to an engineer to avoid the controller from being taken offline, thus motivating our work and increasing the interpretability of a controller. Before I can discuss our modified control strategy, I will first go through a number of slides describing prior work on which our work builds. To begin, we will first be looking at a class of nonlinear systems with the following state space description. The time derivative of the state of the system is described to be a locally Lipschitz vector function of the states, inputs, and disturbances of the system. We assume the system is stabilizable in the sense that there exists a stabilizing controller h of x, which renders the origin asymptotically stable, and there exists a LYAPUNOV function satisfying the following condition. We define the level set omega rho to be the stability region, and it is the level set of V in which state constraints are met. The controller we will be considering in this work uses an empirical model based on collected data denoted by the subscript B. Similar to the class of nonlinear systems which we saw in the last slide, we assume that there exists a stabilizing control law for this class of models which renders the origin asymptotically stable, and there exists a LYAPUNOV function which is strictly decreasing when the stabilizing controller is applied. For the empirical models, we consider the stability region omega rho safe and define omega rho as a subset of the stability region. Traditional economic model predictive control seeks to minimize an economic cost function with respect to a dynamic process model, a state measurement, and input and state constraints. In minimizing the cost function, the controller solves for the most optimal inputs at each sampling period over a prediction horizon, and implements the first calculated input in sample and hold for one sampling period until a new state measurement is received, and then the optimization problem is solved again. LYAPUNOV-based economic model predictive control builds on traditional economic model predictive control by adding two new constraints corresponding to Mode 1 and Mode 2 of operation. In Mode 1, the state is allowed to evolve dynamically within a lower level set of the stability region. State predictions made by the controller in this mode must be within the lower level set. However, with disturbances, it is possible for the state of the actual system to leave the lower level set. Despite this, the state is guaranteed to be held within the stability region if an upper bound on the disturbances is assumed. When the state is outside of the lower level set, or a time has been reached in which it is desired to return to the origin, Mode 2 is implemented. Mode 2 constrains the possible control actions to be those which decrease the LYAPUNOV function over a sampling period, thus bringing the state closer to the origin. If applied recursively, Mode 2 will decrease the LYAPUNOV function until the state converges to a small neighborhood around the steady state. So, between Mode 1 guaranteeing operation within the stability region and Mode 2 guaranteeing the state move towards the origin, it is guaranteed that the state will not leave the stability region during operation. The modified LEMPC strategy described below is by incorporating an empirical process model, which is updated online to reflect changes in the process dynamics signified by the subscript Q. Closed-loop stability and feasibility guarantees rely on how accurate the model is to the process which it seeks to approximate. As the process operates, changes in the process dynamics, including heat exchanger fouling, catalyst deactivation, and process fatigue, begin to accumulate in the system, and inevitably the model will lose accuracy, which might result in the closed-loop state leaving the stability region. In this implementation strategy, the LEMPC is designed to maintain the closed-loop state in omega rho Q, which is a subset of the stability region omega rho safe. When the process dynamics change enough for the closed-loop state to leave omega rho Q, it is ensured that there is some time before it leaves omega rho safe, which allows for the use of a strategy for re-identifying the process model and updating the controller before stability is lost. The ability for the controller to update itself online is a step towards safe and autonomous process operation. Updating a controller online currently is difficult to do in a short period of time before stability is lost. A method for tuning hard-to-design constraints may aid in locating sufficient control parameters without having to rigorously check each one, which may significantly reduce the computation time. For example, the lower level set of the stability region, omega rho E, may be tuned to obtain a sufficient value without explicitly checking. To tune this parameter, the process is simulated for short periods, and when the closed-loop state leaves omega rho E, the backup controller returns the state to the lower level set and decreases the size of the set slightly. We'll be taking a look at a chemical process example in which a continuous stirred tank reactor is simulated with a second-order exothermic irreversible reaction of the form A goes to B. The following state trajectories are used to describe the process model, and the control objective is to optimize process economics while preventing the closed-loop state from leaving the expected region of operation. The LYAPUNOV-based controller used to stabilize the process is designed with an inlet concentration input of 0 kmols per meter cubed. The heat rate input is designed using Sontag's formula. We have a quadratic Lyapunov function of the following form. We have a stability region of rho equals 300, where omega rho E is a subset of omega rho. And then we have the LEMPC parameters of 10 sampling periods and a prediction horizon, a sampling period of 0.01 hour, and we assume measurements are available at every 10 to the negative 4th hour. The goal of the method here is to increase omega rho E to maximize the time of mode 1 operation. We initialize rho E at 0.75 rho, and we increase it by 1 after each sampling period until the Lyapunov function is greater than 0.99 rho within a sampling period. If this happens, then rho E is decreased by 1. Over 1 hour of operation, we found a maximum Lyapunov function value of 297.02, indicating that the closed-loop stability was maintained during operation, and we found a rho E value, which ended up being 293.
Self-updating in control, as described on the prior slide, is a move toward autonomy. But as we do move toward autonomy, there comes the question of how to define interpretability in control design. Typically, we consider this to mean some type of way that enables humans to reason about the actions of autonomous systems. And if they can do that, we consider that that would be an important step for artificial intelligence. However, a key challenge in defining interpretability is the human element. Not all aspects of systems that are run autonomously are necessarily interpretable. For example, we can look at cases where if a human was to look at process sensor measurements, they would not be able to easily distinguish that a cyber attack was occurring. As an example of this, consider the simulation on the right. Here we have a CSTR under a tracking model predictive controller, where the attacker is using a first principles model and inserting disturbances and measurement noise that fall within the bounds expected in determining their attack trajectory. This causes the falsified sensor measurement to look reasonable over time. And in fact, it is actually an example of an alternative simulation trajectory that you would have if you were actually simulating the process under the controller, under different realizations of the disturbance. However, despite the good look of the measurements, the actual state trajectory is gradually over time being driven away from the steady state. So this is a case where a human would not be able to look at this and interpret very easily that there is an attack occurring, because from a simulation perspective, this is a completely valid trajectory. These types of considerations make defining interpretability difficult, in that we have to consider what humans would and would not be able to do or achieve, and how that should impact control design. Because there would then be many definitions of interpretability, we'll look at a specific definition here. A possible definition of interpretability for control would be that humans like the control actions that they see. Controllers then should be able to self-update themselves to improve their response according to end-user desires that they would not be able to know before they actually are online. This would enhance the accessibility of advanced control, but also would require that the self-updates be based on human reactions to the manner in which the controller is operating a process. And challenges with that are that there's uncertainty in determining human preferences, and also human preferences about the way the controller is acting might not be correct in terms of what's really the best thing for it to do. So in order to develop controllers that are interpretable in the sense defined here, we would like them to not impact any theoretical guarantee. So they can't impact closed-loop stability or recursive feasibility. But potentially we could achieve this by allowing there to be some constraints in the controller which can be tuned but which have no impact on the stability and feasibility guarantees, only in the way that the closed-loop state trajectory looks. An example of such constraints is input rate of change constraints. These were originally added in the context of LYAPUNOV-based EMPC with the intent to reduce actuator wear. In the case that they reduce actuator wear, the difference between any two inputs applied to the process is upper bounded. And that is the case whenever epsilon desired used in the control law as a way of enforcing an input rate of change constraint, and the sampling period used in the LAMPC are sufficiently small. However, the epsilon desired can take a range of values in the LAMPC. In the LAMPC, it's a tuning parameter. It's not actually a physical quantity. Because it can take a range of values without impacting closed-loop stability, this implies it could be one of those constraints that might be helpful from an interpretability perspective, in the sense that it could be tuned to respond to human sentiments, maybe something like rankings of the process response for various values of epsilon desired, providing control actions that achieve desired responses while not impacting anything about stability. We can see the impact of this by looking at a continuous stirred tank reactor with the catalytic oxidation of ethylene to ethylene oxide. In this case, we have two dimensionless inputs, which are the feed volumetric flow rate and the feed ethylene concentration. We also have dimensionless process state variables corresponding to the reactor gas density, ethylene concentration, ethylene oxide concentration, and reactor temperature, and the reactor dynamic model is presented here. The control objective is to maximize the average yield of ethylene oxide, where the time average yield of ethylene oxide is given by the expression here. The limit on the average amount of ethylene fed to the reactor over time fixes the denominator in this case. So we're going to try to maximize the numerator of the equation for the yield. We also consider bounded inputs for physical reasons. Here we show the results for using a number of different values of epsilon desired in an EMPC to try to tune the input rate of change constraint. In this case, we are not using an LEMPC, we are not using LYAPUNOV-based stability constraints. So we enforce the value epsilon desired directly on the input trajectories rather than on any type of function related to the LYAPUNOV-based controller. 8 different values of epsilon desired are tested here, and we can see the different ways in which the inputs are being affected by the different control laws that are represented by those different values of epsilon desired. Here we see that in all of those cases, the closed loop state was maintained in a bounded region. We could assume then that perhaps a ranking is made of how operators or engineers feel about all those different responses when taking into account things like the yields as well as potential actuator wear, and then that if the function was to have a shape, for example, like the one shown here in red, that we could differentiate that, find the optimal value of epsilon desired, and then apply it to the process and get something like the trajectories that are shown in the bottom right. In conclusion, it is important to develop controllers which guarantee closed-loop stability. An LEMPC implementation strategy can aid in tuning controllers with stability-based constraints, and this implementation strategy can help to ensure that the closed-loop state never leaves a bounded region of operation, even when it leaves a level set of the Lyapunov function, as certain constraints in the LEMPC are being self-tuned. But rigorous closed-loop stability conditions would still need to be met in order to guarantee stability with this kind of tuning method. Verified safety for control must work with interpretability. Human trust in control actions is critical, but defining interpretability can be challenging due to its relationship to how humans understand the response of the controller. A potential interpretability concept is a self-tuning constraint that tunes itself in response to human feelings about the control actions, in which case those constraints would need to be chosen and selected to be ones which impact only the response of the process, but not stability or feasibility of the controller. We would like to thank the National Science Foundation, Air Force Office of Scientific Research, and Wayne State University for their financial support. Thank you.